Hello everyone, welcome to AI lecture series. This is lecture number 16. In the previous lectures we studied some basic concepts of logic, the Wumpus world problem and prepositional logic. Now we'll combine them and create a simple knowledge base for the Wumpus world using the prepositional logic. So here we have the Wumpus world. So here there are 16 rooms. The agent starts with this 1 1 and finds it's okay. So we have a fact in the knowledge base. So this is the fact R1. It says that there is no pit in 1 1. So this R1 is a fact. This is written here. R1 is a fact. So this square is there is no pit in this square. So this is the fact, and we will now formulate some rules. So a square is breezy if and only if there is a pit in a neighboring square. This rule now we can state by this R. So we have this rule R2 with a by condition. So it says that B11 is breezy if and only if there is a pit in 1 2 or there is a pit in 2 1. So here a thing should be noted that we don't have a single implication here, but it is a by condition. Now why a by condition? Because this breezy B11 is by condition, means both are implying each other, both are true. In that sense, how we can write, we know this A by condition B is also equivalent to A implies B and B implies A. If we apply the same rule here with the breeze, so here if we split this, what we get is B11, it implies P12 or P21 and P12 or P21 implies B11. So this is what we have. Okay. So both are implying, therefore this is a by condition. So if there is a pit in 1 2 or P21, then we will have breeze, and if there is a breeze, that means there is a pit in 1 2 or 2 1. So this is the rule. Then similarly here that what we have seen now is, if this is breezy, if suppose this is breezy, that means there is a pit here or a pit here. That what we have written 1 2 and 2 1. Now suppose there is then we have the rule R3. What does it say? B21. That is, this B21 is breezy if and only if there is a pit over here in 1 1 or pit in 2 2 or a pit in 3 1. So there would be either a pit in here 1 1 or 2 2 or 3 1. So it is with or, means any of them or more than one can have pit. So this is another rule. This is also with the by condition. So this is how we formulate the rule. We'll see some more rules here. Then when let us assume the agent now goes to the region 2 1. So 2 1, when it goes to 7, it senses breeze. So it means this particular this region is breeze. So it means there would be some pit around here. So it adds to its knowledge base. What does it adds to its knowledge base? That 1 1 is not breezy because it didn't sense any breeze here. So this is one fact. Then R5, it added a fact that B21 is breezy. So these two facts are added to the knowledge base. So here if we sum up all the things which we have done till now, so R1, rule 1 is, or R1 says is there is no pit in 1 1, and these are the two rules. B11 is breezy if and only if there is a pit in 1 2 or 2 1. 2 1 is breezy if and only if there is a pit in 1 1 or pit in 2 2 or pit in 3 1. And this is the fact that B1 that 1 1 is not breezy and 2 1 is breezy. Now we'll see a simple inference procedure, which is actually called as a model checking approach. Now given this facts and rules which we have just seen, which are in the knowledge base, so can we infer, can we entail something from that? Like can we say that the knowledge base of the agent entails some alpha, where alpha is like there is no pit in 1 2? Can we entail this thing from the knowledge base? Let's see. Now in this knowledge base, what we see is there are 7 different symbols in the knowledge base. There are 7 different symbols. We see here, I've written here, the 7 different symbols are P11, P12, P21, P22, P31, B11 and B21. So these are 7 symbols. Now the first thing in this case, model checking approach, we draw a truth table taking this inputs, this number of inputs. Now if we have 2 inputs, we can have 2 raised to 2 4 combination. If we have 3 inputs, we should have 2 raised to 3 8 combination. For 4 inputs, we have 2 raised to 4, that is 16 combination. Here we have 7 inputs, so there are 2 raised to 7, that is 128 combinations. So we need to check all those 128 combinations. We have to prepare a truth table, and for each model, that is for each value of this, we will have of course 120. For each value of this particular variables, we need to check R1, R2, R3, R4, R5, and finally take AND of them. So this is our actual output, which is the knowledge base. This is our knowledge base. So let us see what we can entail with this. Now here we are given that this truth table is prepared. Now it is impossible to make all this 127 entries. We cannot do actually 120 entries. There are 128 entries. We cannot do 120 entries here. So this is the first one. This is the first input. All false, 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 false. For this all inputs, what is R1? What is R2? What is R3? What is R4? What is R5? And then we take AND of all this. We AND all them. And see, this is false. Then the second input is false, 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 and this is true, and so on until we reach the last one, which is all true. So for how do we calculate R1? So here you can see actually R1 is negation of P1. So if P11 is true, it is for this R1 become false because it is negation. Then we will, for R2, we take this particular as the inputs. These 3 are the inputs, and apply the rules of bicondition. Then R3, R4 and R5, we all calculate all this R2, R3, R4, R5, and then finally AND them. Now let us give a query. Suppose if we pose a query, can we infer this? Does the knowledge base entails that? Does our knowledge base, does it entails that alpha 1? Does our knowledge base entails, does this knowledge base entails alpha 1, where alpha 1 is a negation of P2? So what do we mean by when to say does our knowledge base entails that there is no pit in 1 2? Now we check the truth. So we check the truth table. In the truth table, the knowledge base is true for only these 3 entries, and for now we want to check this P of 1 2. Now P of 1 2, P12 is this particular column. This particular column. Now knowledge base is true for this 3 only entries, and for this 3 this is false. This is false. Okay, you can see this. So we can for all the truth values of the knowledge base, P12 is false. So it of course we can entail that there is no pit. So because there is false, if it had been true, we could have said P12 means pit in 1 2. So it is false. It means there is no pit in 1 2. So of course it is entailed by this knowledge base that there is no pit in 1 2 by this particular procedure. Then if we pose a query, is there no pit in 2 2? So knowledge base, again we check for P22. For P22 we see some values are true, some value are false. So this is false, this is true, this is true. So for all these true values, P22, one is false, this true, this true, neither all are true, neither all are false for all the true values of knowledge base. So this cannot be inferred. This cannot be inferred. Okay, if we are told even if we are asked whether there is pit in 2 1, it is not given. Remember, if I am saying if there is no, is there pit in 2 1? So here we see for all these true values, this is false. So knowledge base can infer that there is no patent to 1. So this is how the inference mechanism works in with this type. But here the difficulty in this particular procedure is the number of inputs. Here there are only very few inputs are shown. There are actually 128 such entries. Now the number of inputs are just 7. Suppose if we have a number of inputs are 10, 20, then the values, the number of these entries may run into millions. So it becomes difficult to infer in that case. Next we see propositional theorem proving. So we can see entailment can also be done using theorem proving. That is applying the rules of inference directly to the sentences which are in our knowledge base. Okay, we don't need to construct all the models. Like in the previous case we saw there were 7 inputs. So we had to make 128 models. So if the number of inputs are more, then the combination may run into millions and it will become difficult. So we can use this propositional theorem proving. So before using that, we will see some concepts of theorem proving. The first is logical equivalence. So two sentences can be logically equivalent and they are following some rules. So here some equivalence, standard equivalence are given, like the first one, alpha and beta is equivalent to alpha and beta is equivalent to beta and alpha. So both are equivalent. Same way alpha or beta is equivalent to beta or alpha. Then this one, associative law. Then associativity of and associativity of or. Then double negation. If we take a double negation of alpha, we get alpha itself. Negation of alpha is alpha itself. Next is contraposition. Now contraposition is, suppose if we have alpha implies beta. So if we take negation on both the sides, then what we have is negation of beta implies negation of alpha. These rules would be used to solve the propositions. Okay, to these rules, of course, we will use this equivalence relation for getting the entailment. Then here one more, if we want to eliminate the implication, yes, this one. So we can eliminate the implication by using this particular alpha implies beta. It is equivalent to negation of alpha or beta. So here we can see this implication sign goes and we have a or sign. We can prove this, of course, that how alpha implies beta is equivalent to negation of alpha or beta. So here we can do by truth table. So we have two values, alpha, beta, and then we have alpha implies beta, and we also need this negation of alpha, and then finally negation of alpha or beta. We have to prove this. So alpha, beta, these are two values, so we have 4 combination: false, false, then false, true, true, false, and finally true, true. So alpha implies beta is true, this is true. For this true, false, we have this is false and this is true. Now negation of alpha means wherever alpha is false it becomes true and true it becomes false. So we have this true, true, false and false. So we take OR of this two, OR of this two. So the rule of OR says that when both are false it is false, otherwise it is true. So this is true, this is true. Now this one, this is false, this is false, so it becomes false, and here it becomes true. So if we compare these two, they are equivalent. Okay, here true, here true, 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 false, false, true, true. So this is how we verify them. So this is equivalence. Then this by condition can be eliminated, like if we have alpha implies beta. So if we have alpha implies beta, so we can actually alpha by condition beta, this is equivalent to alpha implies beta and beta implies alpha. So this particular by condition can be eliminated by using this particular relation. Of course it can also be verified. Then this is De Morgan's law. Okay, this is De Morgan's law. We are familiar with electronics like this. A or B the whole bar is A bar dot B bar, and we have this A dot B the whole bar is A bar or B bar. So this is what we have. So in this particular case we have, which is equal to, so negation of A or B bracket, so it becomes negation of A and negation of B, and negation of A and B is negation of A or negation of B. Then finally the distributive of or over and over or, and or over and. So these are the standard equivalences. Then second is validity. What is the meaning of validity? If we are given a sentence and it is true for all the possible models of that particular variables, then we say that it is valid. Otherwise it is it may be something else. Like suppose if we have a relation, a sentence like suppose P is given by A or negation of A. So this particular sentence, A or negation of A, is always true. It is always true. So we say this is valid. This is a valid sentence because it is always true for all the values of A. It is always true. So it becomes a valid. Then what is the meaning of satisfiability? Now satisfiability is like if we have a relation, if we have a sentence P equal to A or B, A or B. So if I draw the truth table this here, A or B, and we have A or B. So false, 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 true, true, false, and finally true, true. So I know this, or the rule for all is this is false, rest all are true. So we, in this case, we find at least one assignment of values of A and B which makes this particular sentence true. Even if there is one, then it is satisfiable. It is satisfiable. So it is used in the SAT problems. So if even if a single assignment of AB makes the sentence true, then we say it is satisfiable. Here we are getting three values. For case of AND, we know for AND all are false, the last is true, where both are true too. So this is also satisfiable because we have this true. Now if we have a sentence like this, A and negation of A. Now this sentence is false. It is never true. It is always false for all the values of A. So this is not satisfiable. So this is how we see the three things: logical equivalence, validity, and satisfiability. So here we will see that what we have proved in this case is this particular sentence, if we have a sentence P which is A or B, suppose, so this is actually satisfiable but not valid. Again, A and B, this is satisfiable but not valid because it is not true for all the assignments of A and B, both the cases. So they are satisfiable because there is at least one assignment for which these sentences are true. So these two sentences, they are actually satisfiable but they are not valid. So there is a difference between validity and satisfiability. Now we see some more rules for inference procedure. The first is modus ponens. So what does modus ponens say? That if we are given alpha implies beta, we are given alpha implies beta, and if alpha is true, then beta can be inferred. This is what is given. So we have a rule, alpha implies beta is a rule given to us, and it is given that alpha is true, so we can infer beta. Let us understand this with an example. Like suppose we have a sentence alpha. It says your king is checkmate, and beta is the inference, you lose the game. You lose the game. So we have these two sentences, and we have a rule, alpha implies beta. So what alpha implies beta says, this as we know, this alpha implies beta implication is as good as if then else. So if we are writing alpha implies beta, it is as good as writing if alpha then beta. This is what the implication says, if alpha then beta. So here what it means, if your king is checkmate, then you lose the game. This is what the rule says. according to this. So they are related by this. Now according to this rule, suppose if it is given alpha is true, we are given this rule is there, and suppose alpha becomes true. So it says if your king is checkmate, you lose the game, and it is given your king is checkmate. So we infer that you lost the game. You lose the game. So this is what the inference is. So we infer beta now. So alpha implies beta is a rule, and when alpha becomes true, beta can be inferred. That is, beta can be inferred. Okay, we can conclude beta. So this is the modus ponens rule. Then second rule is and elimination. So if we are given a rule, we are given the sentence alpha and beta. So if this is true, so we can infer that alpha is true. So if it is given alpha and beta is true, so we can infer alpha is true. We can also even that beta is also beta is also true. So we can eliminate this, and so if we are given alpha and beta and it is true, then we can eliminate the and as well as any of the variable. We can write it with alpha, or we can also write it as only beta. Okay, so that's all for this session. Thanks for watching.